there's 12 funding awards. The state of Wyoming also put in an application. I don't know of any others. So that's for $1.2 million. And the end game here is to identify commercial CO2 sequestration sites. So it's enough to talk about capturing CO2, which is the CCC part of this, but if CO2 is captured, once you've compressed it and purified it, what do you do? What do you do with that CO2? And the purpose here is to look at a commercial site where you would inject CO2 for long-term sequestration. Any questions so far? Okay.
Yeah, I have a question. So, where are you thinking about injecting it? I mean, into like an oil well, or?
Well, it would be a separate injection wells or set of injection wells, and we're looking at doing it at the Hunter site because it's over the strata that would be used for the CO2 storage. We'll have a side view here just to get to that. So as part of that whole team is meant to put together as a technical and non-technical evaluation of the regulatory, legislative, and technical policy and commercial and financial risks, which are going to be, pretty interesting as you go for CO2 capture for a long scale. It's to look at the economic feasibility, public acceptance of that, and a technical evaluation of the geology for injecting the CO2. So I get, at this stage, what I'd like to, already.
Where in this is the risk and liability considered? Is that under the funding?
It is, and that's part of the study program is to look at it's not just the technical risk, but it's the public acceptance risk, in terms of CO2 capture. So I'm going to turn it over to Richard and Andrew, if you guys wouldn't mind. This is, if you will, this is their slide to kind of talk through what the phases are. I don't know who's on point between you two guys.
Yeah. So this is the concept diagram that we submitted to the United States Department of Energy as part of the proposal. And we've broken down the pre-feasibility study that is carbon safe into 4 main tasks. The different colors here at the top, blue is task 1. And that's to establish the team, the carbon safe team, to look at the pre-feasibility and to assemble kind of a preliminary list of the technical and non-technical challenges associated with a large-scale carbon capture and storage project. Task 2 is to, really assemble a plan to address those challenges. Technical challenges would be injecting 50 million tons of CO2 into the subsurface, looking at the migration of the CO2 over time, how it interacts with the rock. And some of the non-technical challenges that have been brought up are the economics of not only capturing the CO2, but transporting it and injecting it into the subsurface. A big non-technical challenge will be the public perception of the project. A couple slides we'll be seeing shortly. The proposed site is actually the San Rafael Swell in central Utah. So the blue outline there is actually the geologic outline of the San Rafael Swell. And as many of you know, the San Rafael Swell is it's a kind of a touchy subject in the state of Utah. And we certainly anticipate a lot of obstruction by some environmental groups. Can we go back a slide to the other tasks? So there we've laid out the external challenges, the public and economic challenges, and we'll assemble a detailed plan for looking at long-term viability of the CO2 that we're injecting. Task 3 are the technical issues, the storage of the CO2 into the geology. As mentioned, we're looking at the geology below the Hunter power plant. In particular, there's a sandstone called the white rim sandstone. It's very porous, very deep, has a high permeability. These are all things that we typically look for when we're wanting to inject CO2 in the subsurface. Along those lines, we'll be doing extensive modeling and simulation of CO2 injection, as I said earlier, the CO2 interacts with the rock on the subsurface. And then task 4 is to develop a plan for additional characterization. As Ian mentioned, this is just the first phase of 4 total phases that the U.S. Department of Energy has put out for this carbon safe. Phase 1, the deadline was 2 months ago, August. Phase 2, they've already submitted the FOA, and that is due in December of 2017. And that's additional evaluation of the injection area. Phase 3 and Phase 4 have not yet been made public, but essentially Phase 3 will be a site characterization where you go into more technical detail of the area, and then Phase 4 would be the actual construction of the site. So we can move on to the next. So here we have the San Rafael swell. It's a wonderful area actually for carbon capture and storage. We have proximity to Hunter, but also the Huntington Power Plant just to the north. We have a lot of federal and state land, in this case SITLA, the State Institutional Trust Administration, who have worked with us extensively in the past, and they would be amenable to surface siting of wells and monitoring wells. It's a geologic anticline. Basically, it's a structural geological structure, like an upside-down bowl, that is ideally suited for injection and capture of CO2. As I mentioned, the White Rim is an excellent reservoir. It's throughout the southwest United States. It's thick. It's very deep. High porosity, high permeability, basically a large sponge where you can inject a lot of CO2. Next slide.
Richard, could you comment your background?
Oh, sorry.
I should have.
Yes, my background is I received my degree in geochemistry from New Mexico Tech University. For the last 9 years, I've been here at the University of Utah as part of another Department of Energy funded project called the Southwest Carbon Partnership, where we're actually looking at the feasibility, long-term feasibility of carbon capture and storage within the United States, in particular the Southwest United States. The SWP has a commercial scale injection project in northern Texas where we're injecting approximately 1 million tons of CO2 into subsurface, so this would be a similar project. And in my case, I'm the work group lead for a task that's associated with monitoring of the injected CO2 from the subsurface. So this is just a different view. The green region is the San Rafael swell. We're calling it the San Rafael anticline. And the secondary site is the Huntington anticline just to the north. Move on to the next slide. This is just a geologic map showing the surface geology of the San Rafael anticline. The Hunter plant obviously is there in the left upper part of the slide. And here the scale is, the bottom there you see is, I think, 18 kilometers. So it's, I think, yeah, 35, basically 35 miles across. So it's a large area and it's sufficient for storing. We've done capacity estimates for the entire San Rafael swell for just the White Rim sandstone.
And the black dots are?
The black dots are existing oil and gas wells. This is where we would pull a lot of our subsurface geologic characterization data from. In fact, as part of our existing Department of Energy funded project, we've already done preliminary analysis of the CO2 storage capacity based on data collected from a lot of these wells. And I can't remember the number off the top of my head, but for the White Rim sandstone, we're looking at several 100 million tons of CO2 storage just for this region here. So as I mentioned, it's basically an upside-down bowl. So if you inject CO2 at the Hunter power plant, it's going to basically migrate up dip towards the center of the swell. But preliminary simulations we've done on CO2 migration, we've taken our simulations out to 1,000 years, and I think the maximum migration is about 10 kilometers. So it's still going to remain in the vicinity. And this is just taking that geologic map and turning it sideways, so we're looking at the depths of the different geology. The Hunter Power Plant is the star where we potentially drill our injection well or wells, and the White Rim Sandstone is that thick yellow region there just below the Hunter Power Plant. And again, it's very thick, it's very permeable, highly porous, basically a large sponge to inject CO2. And this is just a geologic cross-section, a compilation of the data that we've collected from those oil and gas wells in the area. And this geology is typical of the geology we see elsewhere on the Colorado Plateau. And again, this is ideal for carbon capture and storage projects. It's essentially a layer cake of alternating seals and reservoirs, which is ideal for injecting CO2. In the event you do have a leak from the reservoir that you're injecting your CO2 into, it's going to migrate up past the seal, but it's going to encounter another reservoir, and then basically a layer of reservoirs and seals. And based on our analysis of the entire southwestern region, such similar geology, we've estimated 250 billion metric tons of CO2 storage is available in our region. Next slide. We're about 8,000 feet, just below the 100 power plant.
That's to the red wall?
The red wall is a secondary reservoir. The White Rim Sandstone is about 8,000 feet. So as Ian mentioned, we've already submitted an application to phase 1 of this FOA that the DOE sent an FOA for. They sent out the FOA in June, so it's a fairly short fuse on the proposal, but working with Ian and others at the University of Utah and Utah Geologic Survey, we put together a very good proposal.
No fairly about it.
Really good chance of being funded. We were supposed to hear by the end of October. The DOE has not yet sent out their notification, so I'm taking that as a good sign. There's a lot of good proposals. So the objective of this is to, as Ian mentioned, secure the $1.3 million as part of that proposal. And it's leveraged with approximately $300,000 of matching funds from this program, STEP program, and the University of Utah. Next slide. In those 2 or 3 short months, we've pulled together an all-star partner list. University of Utah and Energy and Geoscience leading it. USTAR has been helping significantly on a lot of the different aspects. Obviously, with the Utah Geology, the Geologic Survey, the ideal partner. We secured partnerships with 2 national labs, Sandia and Los Alamos. We're going to be looking at risk and economics of the project. Schlumberger Carbon Services has helped us in a lot of different projects, looking at well drilling and seismic surveys for characterization of the geology. The Utah Division of Environmental Quality, as part of any future carbon capture and storage project, we have to follow the new Environmental Protection Agency guidelines for injecting CO2, and they'll be critical in identifying a lot of those issues. And New Mexico Tech, they're our co-lead on our Southwest Carbon Partnership project. They're going to be looking at a lot of the seismic work. The University of Utah Law School looking at the liability issues, obviously Rocky Mountain Power, and then we've already put together a very strong advisory board to help us look at a lot of these other issues associated with the project.
When you inject the CO2, will it be a liquid or a gas?
It will be a supercritical phase, essentially liquid.
It will be liquid.
at those depths and those pressures. Definitely. Next slide. So as Ian mentioned, Rocky Mountain Power would be a co-funding source on that $1.3 million. Any Department of Energy project, you're required a certain amount of cost share, in-kind funding. Rocky Mountain Power, University of Utah will be providing that. And then additionally, Rocky Mountain Power would be providing a lot of the technical input for capturing the CO2. So there's a website there for looking at the FOA if you're interested. And do you want to talk any more about the?
No, I mean, I have a copy of the actual application, and the applications, I think it was limited to 30 pages, which is good news. But there is a definition for each of the partners of what each is going to do. So if you want more detail than what Richard's mentioned, it's there for the asking. And in terms of our participation, our contribution would be $150,000, which is essentially getting leveraged up about $1.3 million. So I mean that's we think this is a really good project and a really good team. So I guess leave it open for there was two questions that came, I think, from the DPU is how are you going to manage what is our contribution and how are we going to want to spend? And I think Richard and Andrew can comment on this. These funds are going to be administered by the University of Utah. They're going to administer in the project, and so they've got DOE kind of oversight in terms of the reporting. So I think this will have a pretty rigorous cost overview throughout the whole project basis. So. And you can, as you will see in the actual application itself, there is a fair amount of detail in terms of the rigor, in terms of milestones, what the timing of meetings are, when updates are going to occur. And so it's pretty well laid out. So before we move on, Joan.
On the university law department, we'll be working on the public acceptance part. Do you have is it volunteer? Are they contributing as well as staff person?
Well, there's two individuals who are going to participate.
Ethan Davies and John Eagle.
Yeah.
Lincoln Davies has a stellar background in energy law, has published some papers on the economics of carbon capture and sequestration. And John Eagle, I think, is already familiar with the Southwest Regional Partnership, has some experience there, so they're both well poised.
Because I think there will be a tough public acceptance.
I understand that when you inject carbon into basalt, it reacts chemically and becomes part of the rock, and it doesn't. Does the carbon dioxide injected in the sandstone, does it remain so that it would outgas if it was exposed to atmospheric pressure, or?
It would initially. It takes a while in the case of injection of CO2 into a saline aquifer sandstone. Mineral reactions do occur, but they're some of the longer-term reactions. The initial trapping of the CO2 would be purely hydrostratigraphic against those impermeable seal layers.
But then over time it does become.
But we're talking hundreds.
How much?
Hundreds of years.
How long did you say, how far would it migrate?
Our simulations showed it migrating no more than about 10 miles in 1,000 years.
That map showed that the outcropping was about 35 miles.
Correct, that's correct. There is an outcrop of the white rim sandstone about 35 miles to the east and southeast. But our simulations show it would never get close to that.
So
And what were the volumes for 10 miles?
I don't remember the rate, but I believe 10 million tons total. But
What does that mean, though? I mean, that means 100 years that we'll be able to keep filling in, or 5 years, or, I mean, how much CO2
It's
are
not,
y'all estimating that we'll use?
well, it depends on the lifespan of the power
Of the
plant.
source, yeah.
The problem is not, the data we have on the White River Sandstone doesn't tell us a whole lot about injectivity. We don't know if we'll be able to get by with 1 well, or will we need 4 wells or 10 wells to inject the volume of CO2 from the object plant. But as far as total capacity, it's at least 50 million tons based on the requirements of the U.S. Department of Energy proposal. Our storage capacity estimate based on the volume of the geology in the San Rafael swell, again, we're looking at several 100 million tons of CO2. So the CO2 output of the Hunter plant is
10 million a year
So
total.
many years.
So, the capacity here, where you said it was 50 million tons, so you were assuming doing this over 5 years?
No, that was a DOE requirement for how they evaluated what a commercial structure had to be, and that was their minimum.
It's probably worth noting too that you guys found some preliminary dogger data that showed the White River Sandstone's already storing CO2.
A lot of the geologic units in and near the San Rafael swell are already reservoirs for a certain amount of CO2, and that CO2 is not leaking to the surface at present. So it's already a good storage unit for carbon dioxide. We're looking at, I think the most we've seen from downhole well data is about 10% CO2. So you'd have to do a volume estimate.
For the entire sandstone?
No, probably just regions, small pockets of CO2. Some of you may be familiar with Savoy Energy outside of Christ. They're producing CO2 from the White River Sandstone to sell to beverage companies and pharmaceutical companies. So there's already commercial volumes of CO2 in the White River that's not leaking to the surface.
Any more questions on the topic of the Carbon Safe project?
Sounds like, just to clarify, well spacing, we don't know.
At this time, we don't know.
I have one sort of question that, since I don't want to go far afield, yes or no would help. When Mid-American took over, remember there was the working group on carbon capture?
I remember it well.
I know, I thought you would. Is any of that applicable here?
Well, actually, there was during that IGCC working group, we had a number of, Steve Meltzer came in, and we also had, with Idaho National Labs, we had a number of presentations on CO2 capture, but it was not specific to this particular site. I mean, there were other locations. Well, there was, at one time, SoCal Edison was looking at an IGCC project at Woodside, which is on the other side, and so they were looking at CO2 injection there. I think we were also having discussions with UW as well as looking at the Rock Springs uplift for CO2 capture. But I don't think we had any presentations specific on, this west side injection concept.
So you mentioned...
Ask Carol, she was there.
I was there too. I just didn't know if you could move it forward to this.
Is Rocky Mountain Power partnering with University of Wyoming as well on...
We are.
Yeah, so it's hopefully...
Because the Rock Springs uplift is another great location for CO2, and they are doing a lot of characterization work up at and we're adjacent to the Rock Springs uplift is adjacent to the Jim Bridger plant. I mean, but a different team. We ready to move on? Okay, so we're going to move into the what we call woody waste co-firing or biomass, where we're taking trees or leftover trees on the ground floor, process them, and either, we're looking at two different processes here. We have folks from both Ameren Energy, Ralph Coates and his team, and Russ Taylor from AEG Coal Switch, which is their rapid steam expansion process, which sounds a whole lot better than steam explosion. So looking at two 18-hour tests, that doesn't sound like a whole lot, but it takes a long time to accumulate this much material considering the size of the 100 plants. So after we've done that, and again, the idea is to look at material that has a look and feel like coal. I'm going to let each of the Dr. Eddings here and Ralph and Russ kind of walk through what's going on. And right now, we actually have a little study ongoing with the University of Utah where we're testing the milling capability of this material to make sure that this thing goes through a coal mill. Okay? Again, we're looking at testing a Hunter Unit 3, space available over there on where there was a fourth unit conceived, so there's a little bit of space on the third site. You guys blaring or?
The left is Hunter Unit 3.
Hunter Unit 3, third one on the left. So what I'd like to do, I don't know if Eric or Ralph or who wants to?
I'm happy to do that.
Eric, would you like to?
Sure. So as Ian mentioned, there are a couple of different technologies that are being evaluated for their viability for basically upgrading this woody biomass that in its original form has a low energy density. The amount of BTUs in a given volume of material is relatively low when you just pump the material from the forest floor. And so both of these processes will upgrade the material, make it more coal-like, so that when we co-fire it with the coal in the power plant, and also transport it to the power plant, it's much more energy efficient, and the carbon footprint, if you will, of the process of getting this material to the power plant is much lower. So the schematic that you see in front of you is the schematic of the Ameren Energy technology. Basically, the biomass material that's been passed around, the loose, fibrous-looking material that you see, is fed into a rotating kiln, a tube, where there are a series of burners along the bottom, as you can see there, the little flame-looking icons, and the material is heated to relatively low temperatures between 200 and maybe 325 degrees Celsius. And that heating process will break down the molecular structure of the wood and drive off some gases and vapors that we collect and recycle and burn as input fuel to the process. The solid material, the char material that comes off then is the product that is used, is torrefied wood, as it is referred to feed into co-fire with the coal. So it's a thermally processed coal that will grind and has a higher energy density than traditional wood. If you want to, next slide. So the process that Ameren has been developed was initially developed at a laboratory scale. There was a recognition that because the biomass material is produced over a wide geographical region, in order to minimize the shipping of that material, this technology was adapted into a mobile platform so that the technology could be taken out into the field, into the forest, and that's sort of the images that you see here. And then as part of the technology development, next slide, Ian, this was scaled up to the current size unit, which is about 20 tons per day, where some field demonstrations have been carried out just over the last 18 months or so. One more slide, where it's a little hard to see, I guess. On the left is just a large pile of biomass material, again, similar to what you have seen, and the output is large super sacks of more energy-dense material that can then be shipped more efficiently to the site. The AEG chemicals, which, Russ, would you prefer to talk this, or I'm happy to do that?
That's great, I can certainly do that.
Okay.
So, let me take just maybe a minute and give you a little background on AEG. AEG is Active Energy Group. It's actually a company based out of the United Kingdom. And it's a energy/environmental company that manages over 7 million hectares of forest throughout Canada and the UK. And one of the largest forest management companies, frankly, in the world. AEG, and maybe I can grab this sample right here. AEG, as they've worked forests throughout the world, they've learned that you've got to manage a forest to have a healthy forest. And we've seen, especially in the last couple of years, the major fire that just happened in Canada. We've got fires that are going on in California, fires throughout Utah. The one that we just happened down here in central Utah was our pinyon juniper burning out. If you don't manage these forests, they die, beetle kill, ends up on the ground. One of two things happen. Either they rot, and if they rot, they turn to methane. So most of this meeting's talking about CO2 capture, yet if we have millions and millions and millions of metric tons of hog fuel waste, slash, we've been doing agriculture and timber industry around the United States and Canada for the last 200 years. And if you were to go out and look at what's out there, there are hundreds of millions of metric ton of material sitting in piles. They call them legacy piles and heritage piles, and they're rotting. And as they rot, they're producing methane. Methane is 32 times worse than CO2. So, we attack what's coming out of a coal plant, yet we're pumping methane into the atmosphere all over the world, and we're really not doing anything about it. And that's where AEG came in, is they said, how do we take these waste streams that are there and turn them into something that's valuable? First off, we have a product that's carbon neutral, and technically, it's a waste product that is hazardous if you don't take care of it. Second thing that we're doing is we're mitigating fire. If you look at Utah, we've got pinyon juniper problems. In the last 150 years, pinyon junipers expanded over 250% in the state of Utah. There's money being thrown at it left and right to go out and deal with sage-grouse habitat, go out and deal with different rangelands for animals, and yet the water problem is probably our biggest issue. If you have a canopy, what they call a PJ3, if you have a canopy that's a stage 3 canopy, between 21 and 60% of the moisture, whether it comes from rain or from snowpack, never makes it to our aquifer because the junipers pull it out. So when people talk about biomass, one of the things as I read Biomass Magazine, as I read most of the people that are adversaries to that particular type of feedstock, they're thinking we're going to go out and cut down forests, good trees. That's not the case. What we want to do is manage the forests that are there and use waste streams that are out and creating a hazard and deal with it and turn it into something that's productive. And as Ian just mentioned earlier, what AEG has done is we've tested all types of materials throughout the United States. Matter of fact, over at our lab here on California Avenue, we're testing material. We have 4 super sacks of material here from Malaysia. So again, this is a worldwide problem, not just here in the U.S., not in Canada, but it's everywhere. And our goal when we started at AEG and with Biomass Energy Enhancements, which I'm a founder of, we merged the two companies together, was to create a direct drop-in coal replacement for the power plants. Meaning, no money spent to upgrade any of the material handling equipment. You literally take it and drop it in. So what we're doing is we're taking what Mother Nature takes millions of years to do, and we're doing it literally in a matter of minutes, and creating a high carbon, very, very dense material, and yet it's cleaner than coal. Because part of our process is we wash out all of the impurities, if you will, the things that you don't want burning in the coal power plant. The phosphates, the salts, the things that are entrained in a cellular level in a tree, we get it out, and then we turn it into a pure carbon product. So the slides that we have here are really just showing the before and after. We talked about steam expansion. We call it a popcorning effect. We literally blow up the material at a cellular level, open up the lignin, and allow us to go in then and clean out, wash out the entrained material, and then turn around and turn it into a high density. Next slide, Ian. These are junipers that we are harvesting. We're doing it in Nevada. We're doing it here in Utah. This is a legacy pile that exists. There's about 20,000 ton of material sitting in this pile right here, rotting. It's been there for 5 years. The customer called us and said, can you help us nobody's attacking them for pumping methane, but yet they, in their own conscience, said, look, we need to mitigate this, we need to deal with it. And so we're working with them now on processing material that's been sitting and turning it into a valuable product. Next one, Ian. And this is a finished product. This is actually a super sack of this material. As you watch these go around, this is actually Juniper Pellets. And then these are material, this is a material that we actually did for Rocky Mountain Power, which come out of the forest here. And it's a combination. It had aspen in it, it had fir, it had different types of pine, and it was a slash pile. It was just material left there from agriculture harvesting and or beetle kill. We shredded it up, no special, and it's what Amron processed, it's what we processed, and these are the different products that we have for you guys to take a look at. And again, if you have any questions, this is what it starts out like, raw material sitting on the ground. When we do our steam explosion, it ends up with this product here. It actually just looks like you've got mulch coming from Home Depot or Lowe's or something. Matter of fact, we've actually put this in the ground. It's a phenomenal mulch. But this is what it looks like as it comes out of our process, and it goes from there right directly into a pelletizer, and that's what it looks like once we're done with the pelletizer.
So Russ, can you talk about you guys are sharing facilities with?
Yeah, we have a facility over. We're on 9th South and 34th West.
Could you talk about your sharing facilities with Amron Energy as well?
Yes, yeah, we're both in the same location, and our whole goal, both companies, frankly, is to do something good with something that's, quite frankly, a harmful issue, and nobody's really focusing on it. And I would just challenge people to really look at the numbers. Look at how much CO2 goes into the atmosphere when there's a forest fire. How much damage is being done with the methane that's out there, and yet nobody's even looking at that. So, it just...
And part of our scope of work with the University of Utah is actually to look at PM emissions associated with uncontained forest fires. Because, we talk about the CO2 part, but the PM emissions are pretty large, and Eric, you can speak. Carrie Kelly is, she's been she's done a lot of research work in terms of PM emissions from wood smoke and wood fires, and so that's the part we kind of want to address, is that if you can mitigate doing either controlled or uncontrolled fires, because that's what we end up doing right now, is we have a controlled fire, to get rid of the waste product. So we think this has a PM emission benefit as well as the CO2 discussion, which is usually interesting.
You may get into this later, and that's okay if you are, but how does the heat rate compare burning this?
The heating value of this fuel is about 10,000 BTUs per pound, which is slightly less than our coal, which is about 11,700, 11,500 BTUs a pound. So it's pretty close. We think the boiler's not going to know.
And how does the cost, I guess, is there a commercial market yet for this and other markets? Does the cost compare?
Well, for our particular product, I can't speak for Ralph and them, but for our particular product, one of the biggest markets we have right now is the home heating and commercial heating pellet market. Right now they use wood pellets, white wood pellets, which is heartwood. So the people who are like arbor pellets and white flame and people like that are out building these pellets for your pellet stoves, and I talked to actually somebody at the start of this meeting about that. The highest heat on the EPA level, they call it a PFI rating, the highest heat level is about 8,000 BTU. Our pellet's 10,400 BTU, so we're 20 to 25% hotter than the hottest pellet on the market in existence today. Number two is we're probably 30 to 40% cleaner because we've removed all of the harmful things, if you will, inside of the plant material before we pelletized it. And the last component to that is the market. We're using waste stream to build our product. Whereas these people, in order to meet the EPA standards for pellets, have to buy the cleanest, most pristine heartwood. So they're out competing with the lumber companies, people that are building your 2x4s and so forth for their material. So from a cost standpoint, it costs me money to produce my material, but at the end of the day, the value, 20% hotter, significantly cleaner. A ton of pellets at Home Depot, $269 a ton. We're commercially wholesaling this product at $180 a ton. So there's great margin for them.
So that's about $9 a million BTUs. Because everybody here, I think, thinks a lot in terms of dollars per million BTUs.
I see pellets coming between $6 and $9 a million BTUs is sort of the commercial range right now. When things start to get scaled up, hopefully we can see some economies of scale that can push that cost down a little lower, because I know what coal costs.
You have a question?
Yes, what do you do with this material that you wash out of your fibrous material before you pelletize it?
It's a great question. What we do is we actually distill the material off and we create a fertilizer out of it. So the plants soak this up over the years and utilize it as food. We then separate it from the water and we turn it into a fertilizer product. And the water, we actually make water. We're water accretive. When we get the material, it's between 20 and 50% moisture. When we're done, those pellets are 3% moisture. That's what they've stabilized at. And so we make water when we're doing what we're doing. We go into a market, and the water when we're done is surface dischargeable. It meets all the specs.
And then you have fertilizer to sell on the side too.
Fertilizer that could be potentially sold on the side, yes. We're actually in the process of putting a facility in here in Utah on a farm, and they're going to utilize our water stream to actually irrigate their crops and fertilize their crops. So nothing's wasted.
Russ, you want to talk about your
this is our reactor. This is not the scaled unit, if you will, that we will put in. Our reactors, when we designed this system, we designed it to do 40 ton an hour to handle a commercial plant to support utility scale type situations. However, here in Utah, we're having a little bit of a challenge getting enough feedstock to support a 40 ton an hour plant, so we're actually deploying two 10 ton per hour plants in two different places here in Utah. This is our demonstration scale, which is here in Salt Lake, like I said, on our site at 3400 South, 9th South and 3400 West. And we process here, on average, about a ton a day of material. We're doing samples from all over the world. At the end of the day, it's interesting. It doesn't matter what the feedstock looks like coming in, and the palm fronds and palm fruit bunches that we're getting from Malaysia are really nasty. Somebody wants to come over and see something that's nasty. It looks like somebody skinned a monkey and then threw it in a bag, and it's just all wet, and it's just disgusting. And yet, when it's done, it all looks like this, and when it's pelletized, it's pretty much the same. So it doesn't matter what type of woody waste, we pretty much do the same thing with it. And in the end, we have a nice high BTU content, coal replacement product.
What's the ratio of the energy input?
Our energy balance is real high. We actually create about 40% of our own fuel to run the system, off taking the light volatiles off the system itself. So it's very significant. We're extremely efficient. As far as your ratio numbers, it depends on the material I'm processing. Every one of them has different, your light volatiles, your VOCs that you're pulling off have different values to them, so it just depends on the process. And again, this is a hog fuel that we utilized up here, similar to the Pinyon Juniper, and we've got the as-received 4,200 BTU. When it was beneficiated, 9,000 BTU, so we increased that 115%. And again, we pull out all of this is the stuff that, if it's in the material and it was run through a boiler at a power plant, it creates slagging on the inside. They don't want glass on the inside of their boilers. And when we're done, we've reduced it by 70 to 92% from where it started. You don't want chlorine in there, you don't want the phosphates and the salts. And so that's the process that we utilize, and it's unique, that frankly, to our knowledge, there's nobody doing it in the world the way we're doing it, so.
And just so everybody, that 9,000 BTU number is on a lower heating value basis, so that's about 10,000 on a higher.
And it just depends on the material.
And how far you take it.
And how far we decide to take it, exactly, so.
Question?
You mentioned you're having a hard time finding the raw material. You anticipate that being a problem here in Utah in general?
So 70% of our state is federal. Matter of fact, tomorrow morning at 9:30, we have the biomass coordinator from the United States Forest Service coming over to our facility to meet with us. That is a challenge. They don't want you on their land harvesting. In most cases, they would rather do a controlled burn and burn it and deal with it that way. And frankly, why we don't have an absolute outcry from that happening, but utilize that material, we can turn it into something valuable. But again, it's an issue with access. It's an issue that so much of our state is federally controlled and we don't have the access. Where we're having tremendous success is where we have private landowners or state. The state's been phenomenal to work with.
So you have the waste is there for you, but just gaining access to it is the issue then?
It is an issue. There's right now, just in beetle kill in our national forests, there's close to 13 million bone-dry ton of material sitting on the ground wasting. And there's studies that, the Forest Service does the studies, matter of fact, it involves University of Utah, Utah State, and BYU, all of these, they engage everyone to come up with the studies. They just, right now, don't allow private parties to go in and harvest at the scale we need to. There are timber harvests going on, but that's mainly for the logging industry to utilize as timber, through the sawmills. Nothing to support a vertical, if you will, such as producing a coal alternative.
I think the OED's trying to do some work on a federal level.
OED's doing a phenomenal job.
To try and help get over that hurdle.
Yeah, Jordan and Larry and Cameron and that whole crew, Dr. Lahr's team, which, is doing a phenomenal job trying to open that up.
Because I would think traveling back east, the forests grow, if you don't cut the trees back, they're going to take over your property.
Yeah.
Here, that's not the issue so much. You have to cultivate it or it's going to die. So I was just wondering if the waste was there to be able to support this program going forward, or if you would soon run out of stuff to burn.
The waste here is there, but I don't think the waste only is going to support it long-term. For example, one unit at the Hunter plant, what are you burning per day? How many ton, Ian?
14 gallon ton. Well, for all three.
So I can make 40 ton an hour with one plant. I think we ran the numbers on Bonanza, just to give you an example. It would take 7 of our facilities, 7 units, to support the Bonanza plant at 100%. And so that's 7 times 40, you've got 280 ton an hour of material that we're making. To make 280 ton an hour, I need almost 600 ton of raw material per hour to support that. So it's substantial.
And one thing is, we're really only looking at this as a co-firing fuel. We're not looking at 100% diet in these boilers. So we're probably looking at 10% range, and we're also looking at it and doing this on a periodic basis. As the forests need to be cleaned out, then we would process the fuel, and then what we want to know is we can do this in our boilers and it's not an issue. I mean, we don't have a vision that Utah is this great biomass feedstock and we're going to be able to fire 2,000 megawatts with 10% biomass. That's not the plan or the vision.
Have you received any pushback from, when I go backpacking, they're always like, use a stove, leave the stuff sit there and die and decay and become part of the dirt. Don't cook with a fire, use your stove. This seems to be a little bit contrary to that thought. And I would imagine, could you have some pushback on
Well, it depends on who you're talking to. If you're talking to some of the environmental groups, I think they have that attitude. But frankly, if you talk to a forester or somebody who's managing the forest, they realize...
It's not going to be dirt, it's going to be a forest fire. You have a
That's correct.
A forest fire or using it.
Which is natural, but again, if we're here and we can manage the forests, we're managing forests right now in Canada, and we have 7 million hectares on just one of our farms, and it's a 25-year harvesting cycle. So they literally cut and then rotate through that, and in 25 years it's ready to cut again. And we're teamed up with the Métis Indians up there.
They're the ones managing the land. It's some of the most healthy forests that exist in all of Canada right now. And so it's one of those things where it depends on who you're talking to.
Just a question, has this been demonstrated in other areas then?
Yes. But not with these two fuels.
Not with these two fuels?
Right, and not Utah-based fuels. So people have done co-firing studies for quite a while.
They're
The Boardman plant is
pellets.
looking at 100%, the Boardman plant is looking at 100% firing study.
Yeah,
Which
we're
is
doing
a
samples with Boardman
huge,
right now.
huge endeavor in terms of getting enough material for, and I think they're looking at I don't know, is it a 1-week study or 1-day study? It's still
Yeah.
just mammoth.
It's 1,000 ton well, that's a day, so.
It's huge. So in terms of our project team, the Hunter plant from Laren and Mr. Bruno, our corporate technical services would be involved, resource development, so we'd be involved with the fuel procurement part of it, the fuel handling at the plant, the test management and data gathering that the University of Utah and Brigham Young would be needing. They're involved with the test design and some specialized instrumentation we want to install, an assessment, monitoring, and reporting of the results. And also, as I mentioned before, we want to do an air quality assessment on the particulate emissions. And then Ameren and AEG Coal Switch, we look to them for acquiring the raw material, doing the fuel processing, and delivering the fuel to the Hunter plant. Quick look at our budget. You can see here, there's a fair amount of dollars devoted towards the actual biomass fuel and processing. We think those are kind of outside numbers. We will work on the suppliers. You guys get that? Okay. So anyway, that's we're looking at about $790,000 for this total budget period. We endeavor to do the work in late 17. That would give us enough time to acquire the fuel, get it all ready. This is only 2 18-hour tests, so we want everything to be well prepared. Do the test probably in Q3, Q4 this year, and then the following year we'll do the reporting on that effort. So that's, our next topic is the cryogenic capture, and Carol and...
Yeah, just one question, when you do your test, will you be doing you'll be doing air quality analysis when you do that testing?
I mean, we have continuous monitors already. I mean, that's...
When are the planned outages for that plant? Like it's early March or April?
It's 2020 for Unit 3.
Okay, it's really that. So you won't have a chance to actually look inside these plants or anything afterwards? They're just going to keep running?
If we have a tube, we could go and look at that issue.
So what were you thinking? That
But the optimal time to do one of these tests was the day before a plant outage.
Oh.
Just in case.
Yeah.
I like the way you think.
Yeah, as Ian mentioned, co-firing studies have been done at a number of power plants at this level. We've also done at a pilot scale at the University of Utah tests where we've fired at this level and above that, and that sort of composite data has indicated that at these levels, at 10% biomass co-firing, there really shouldn't be any problem with regard to what you might be wondering, deposition and other issues. So based on that, we're quite confident this should.
In addition, there's a part of a task there to install specialized instrumentation on the boiler during the co-firing test, which will provide some feedback on how the particles are behaving inside the boiler and how they're building on the tube surfaces. So we should have valuable information there as well.
So maybe that's getting at the question I was going to ask. Since these studies have been done in various places, what are Pacific Corps' incremental concerns or issues? looking for?
Well, A is throughput through the milling, through the plant itself, getting it into the boiler, just treating it like coal, and the other is the slagging and fouling issues inside the boiler. I mean, those are the things that the operator is contending with all the time is, what's the coal quality? So we really are concerned about the simulated coal quality with this material. We're about ready to move on to our third topic. We either take a short break or just keep on going through it. What's your pleasure? Press on. Okay, so this is the cryogenic carbon capture demo. It's going to propose to do this probably at Hunter Huntington. Again, like I said before, likely with the Hunter plant. We have Dr. Larry Baxter here from Sustainable Energy Solutions. Dr. Baxter is also a chemical engineering professor at BYU. And he's got one of his employees with him as well. The idea is to do a long-term study at the Hunter plant or Huntington, and by that we mean on the order of 6 to 9 months of continuous run. But I think, and I don't want to speak for Larry about the reasons for wanting to do a long-term run with this technology. Larry, you want to just step right in here and take over?
Give you some background on this. So this is a carbon capture technology that shows great promise to reduce both cost and energy demand for capturing CO2 from our power plants or any continuous CO2 source. We've been scaling this up for some time now. We have actually tested twice at Rocky Mountain Power Facilities and the Dave Johnson facility this technology at skid scales. We'll show you some pictures in just a minute.
Sophie?
Thanks so much. Sorry to interrupt. Larry is very hard to hear over the phone. I'm wondering if he could come closer to one of the
closer to the speaker. Is this better, Sophie? Can you hear me better now?
Thank you so much. Yes, thanks.
We miss you, Sophie.
Most people I know don't want to hear me, so you.
All right, thanks.
So as we scale this up and do longer and longer term tests, we start running into issues that only manifest themselves at long term, materials issues, some other kinds of tests. And so our next step is we are in the process now, and what this proposal is about is to work out all of the things that we anticipate are going to be an issue for 6 months long kind of tests, and then build and test this facility, make those modifications in the skid scale systems, and test the facility. In parallel with that, we will be developing a proposal to DOE to build what would be a commercial scale CO2 capture facility in any application other than power plants. And so it'll be on the order of 100 ton per day CO2 capture system. So we go through this slide here. There are key aspects of this technology. We want to make sure, so one of the critical things that often doesn't get talked about with carbon capture technologies is any technology that compromises the reliability of a boiler will have severe economic consequences because of that reliability impact that probably exceed the cost of the carbon capture, actually. So we have put a very high priority on making it a highly reliable process, and that's one of our highest demonstrations. We have already demonstrated that it captures not just carbon dioxide, but SOx, NOx, mercury, particulate, just about every other pollutant except for carbon monoxide, and we want to take some time to study that in more detail. We've demonstrated that in the field. There are a couple of outstanding issues there, especially with respect to NOx, that need some more analysis. The main thing we want to do is get to this long-term testing, 6 to 9 months. We test it as long as we can in the facilities that we've tested so far, which are on the order of 60 hours, up to 60 hours or so, but we need a continuous source of CO2 that we can test for many months. We think that those tests will help us secure about a $25 million grant from the Department of Energy to build a commercial scale system and demonstrate that. We will also be, one of the EPRI's roles in here is doing an independent techno-economic analysis. They've actually already completed one of those, as have a number of other people. Their work and our work both suggest that this is half the cost and a little less than half the cost and half of the energy that it takes to do carbon capture by any of the other technologies. And so that's why DOE and EPRI and others are excited about this. But they will continue in that role, doing that independent analysis. And then we'll do specific case studies for Rocky Mountain power plants. So every site is a little different, and depending on site characteristics, we will look at how, and Tri-State is also a partner in this, we'll also look at the Tri-State plants. Interestingly, just because of the nature of Tri-State as a rural electric cooperative, and hadn't appreciated how much difference that makes in the cost of capital between places, but this technology looks even better at Tri-State because the capital costs are so low, so the costs of capital are so low. So the way the process works, if you just follow this diagram from the left.
I was just going to ask a couple of questions. I think I forgot one. Yeah, I'm assuming that you're going to choose Hunter or Huntington, and it's going to be one unit.
Yes.
Is the goal to try for the 6 to 9 months to capture 100% of everything?
No, that's a good question. So that would be a very, very large facility to capture all of it. So this is a slipstream system. Okay. We'll pull a slipstream off and capture. In this case, we actually do produce an actual liquid CO2 product. It's so at the end of the process, we'll have about 150 bar pressure liquid CO2 stream that will be the product from this.
And this is about 1 ton an hour?
About 1 ton of that per an hour, right.
So I guess that does lead to my next question.
Oh, sorry.
What do you do with the byproduct, or the product out of this? Is it commercially viable to do something with it, or is it, what do you do with it after?
So it is. In small scale markets, CO2 actually commands a pretty high price, and so this would be commercial right now in those small scale markets. But the reality is, so the right way to think about this is if we ever get to the point, no matter what technology you use, if we get to the point that you're capturing enough CO2 to make a difference to the climate on the planet, there will be far, far more CO2 than any market can absorb. So, but initially, at least for niche markets, there's actually some significant opportunity to supply some pretty high-valued product.
So what do you do with it if there's no market?
That's when we come back to the
catch and release.
Come back to where we started today, and that's we sequester it underground, and that's where the great majority will end up. So.
You said you're also capturing the SOx and NOx and mercury. Is this slipstream also going to capture some of that, and will you be able to separate it out? Or
so we've already demonstrated that at the Dave Johnston plant in Wyoming. We showed that the amount of mercury that comes out of the flue gas after it goes through this process is significantly less than the amount that's in the air we breathe. So this is truly clean coal technology. The air is cleaner when it comes out than it is when it goes in some respects. So we will continue to capture that. Mainly so we've demonstrated already that we capture it. We understand quantitatively how the mercury, the SOx, and how everything except the NOx is captured. There are some chemical issues with respect to the NOx that need some more investigation, and that's what we'll be looking at in terms of the pollutants.
Okay. You said the cost have been determined about half of original projections.
About half.
Can you tell us what the cost per ton looks like?
Yeah, so about half of the alternative processes. So we benchmarked this with amine-based systems, which is the kind of the standard system that you would use to do this capture. They come in depending on, so right around $80 per ton of CO2 avoided, 80 to 90 is their numbers, come in around $40 per ton of CO2 avoided. And the energy costs, our energy costs are around, I don't know if these numbers mean anything to you, 0.7 gigajoules per ton, and that's a little less than half of what it takes to do this by an amine process.
If you look at a commercial amine process, it's probably about a 20 to 25% energy penalty, as well as the capital cost.
So to put that in perspective, everything else you do at the plant is a 5% energy penalty, all the other pollutants and everything else you do. So CO2 by itself is 5 times bigger than that, and that's a pretty staggering energy penalty. That, frankly, is why I think we're not building these, as people just can't get their minds around that big of an energy penalty. But this technology comes in at half that, which is still a big energy penalty, but it's actually quite close to the minimum theoretical energy penalty you can get to. You just can't do this job with too much less than that. So any other questions before we step through the flow diagrams? So there's a couple of versions of this process. The one that you see here is the one that we are proposing that we would use for this demonstration. We call this the ECL, or the external cooling loop version. So the flue gas goes through this process without being pressurized or depressurized, aside from just pressure drop things. The flue gas starts out, we cool it down to room temperature, and then, not shown there, we dry it out. So most of the water we remove just by cooling it down to room temperature. The rest of the water we removed using standard technologies. And then it goes through this first, what you see labeled there is heat recovery. And so the flue gas that's coming in is cooled down primarily by the flue gas that's exiting the process. So we warm that flue gas back up to room temperature, but cool the flue gas that's coming in down. In the process of doing that, the CO2 condenses, just like in almost always a blizzard, and that is just like in a blizzard, when the snow condenses, it forms a solid. This CO2 will also form a solid. Turns out, for interesting chemical reasons, you can't get CO2 into a liquid phase at any temperature or pressure at the concentration that it exists in flue gas. And so it's either a solid or a gas, and we cool it down to the point where it forms a solid. We separate the solids from the gas. We then squeeze all the air and everything out of the solids, pressurize or compress the solids, and warm them back up with the gas. Everything warms back up nominally to room temperature, and we have a CO2 stream, which is in the process of warming up, the solid CO2 melts, and now, because it's pure CO2 now, it is liquid CO2 at quite high pressure. And it's delivered at the pressure that would be normally used for CO2 injection in an aquifer or any other application for CO2. Other large-scale applications that CO2 is about $40 a ton valuable for injection for enhanced oil recovery and a few processes like this. So this is designed to be the CO2 that you could put into a pipeline for enhanced oil recovery. Or you could use it as an injection feedstock for the carbon safe program, for example. The other stream is just what we call the nitrogen-rich gas. It has nitrogen, has a little bit of oxygen left in it, and almost nothing else. And that gets vented back to the atmosphere. So that's at atmospheric pressure. So I don't know if there are any questions about all of that. Essentially, you just cool it down until the CO2 forms a solid. Separate the solid from the gas, warm everything back up again, integrate the heat so that you don't waste a lot of heat, and it's pretty much that simple.
So the issue with the NOx has to do with the release of nitrogen and oxygen gas back into the atmosphere and how that interacts, or what are we?
No, the nitrogen that we release is molecular nitrogen, so the NOx forms, so at cold temperatures, the NOx tends to form NO2, and we capture 100% of the NO2 essentially that it forms, but some of it remains NO, and that is instead of NO2. And the kinetics of the formation of NO to NO2, interestingly enough, this is the only chemical reaction I know of that behaves this way, but the kinetics, the reaction goes faster the colder you make the gas, and so almost every other chemical reaction does it the opposite way. So Air Liquide was the first to discover that kinetic, interesting thing, and we just need to get a handle on that to be able to predict the NOx. But the NOx is a small part of this. You wouldn't build this process for NOx capture by itself. It's too expensive. But if you do build it, it does NOx capture, and it does SOx capture, particulate, mercury, just about everything. It does not capture carbon monoxide, but we have essentially no carbon monoxide emissions from these power plants.
So, but the gas you are releasing is, like you said, N2 and O2.
Right. It's basically what we breathe, except the combustion process has taken most of the oxygen out of it, so you do have to make sure it gets high enough to mix with the air before. It's not safe to breathe because there's not enough oxygen. Okay. It's the same.
Low oxygen. Okay.
So these are the skids that we build. We have a couple versions of this process. We build them into these shipping containers. They have been tested at power plants, at cement kilns, at heating plants, at research reactors. They've been tested with biomass and natural gas, coal, both bituminous and subbituminous coal, with shredded tires, with just about every fuel in most locations. But these tests tend to be relatively short-term tests. And so the next step is to make these into very long-term tests so we can look at the long-term implications, especially reliability issues associated with long-term processing. This isn't like a lot of other processes. There really isn't another process like this that you can benchmark yourself against and say, other people, nobody does this. And so we want to make sure that when we build a commercial scale system, that its reliability will be very high so that it doesn't compromise a power plant reliability. And that's really probably the most important thing we'll learn from doing these tests. So in the picture here, you just see us unloading the third of 3 skids that were being tested at I think that's the Dave Johnston plant. That particular one was up there for several months, and the other version was also up there for a few months. So we will use this, actually the other version, not the one that you see here, in the long-term test. We're going to modify it and then use that as a test basis. So there's relatively little new capital equipment involved in this project. It's mostly working out everything we can to make it more reliable, rebuilding the parts that need to be improved, and then doing a very long-term test. So the benefits, I think we've mentioned half the cost and energy of existing alternatives. I didn't mention this. This is really actually very important. It's a retrofit technology, so you don't have to rebuild the power plant in order to make this work, which means that it's much cheaper than if you adopt a technology where you have to build a new power plant first. The power plant costs way more than the carbon capture plant does, and so this could be retrofit on any of Utah's, actually of the world's power plants or CO2 sources, and works as a bolt-on retrofit technology, and it robustly handles essentially all of the criteria pollutants except for carbon monoxide. So it reduces all of those in addition to CO2, reduces them below current new source performance standards, so they're with the possible exception of NOx. So this is our project team. So Pacific Corp will be involved in one of the plants, which to us, we really don't impact the plant much at all. We just need it. We need power, and we would like to have water, but if you don't have water, we just need a little more power, and we can do our own water. And we need flue gas and a place to park and access to the menu room. So
we have those things.
So Pacific Corp is involved in helping us in some important ways aside from just being a host. So helping us to look into how this would actually work in a commercial facility, looking at permitting issues that would be required for doing summary reporting to scale up. You can see the other main partners there. NRECA is mostly in an advisory role, but Tri-State, working with NRECA, is doing some of the environmental health and safety assessments. They're doing a formal safety analysis and environmental impact analysis, also doing advising. EPRI is doing techno-economic analysis and modeling independent of us. We are also doing that. Sustainable Energy Solutions is the main, so we'll be building the equipment, troubleshooting it, and running it. Not listed there is Brigham Young University in the Rocky Mountain Power portion of this project. They're not involved, but this is part of a much larger project in which BYU is involved which is where my job is actually at BYU, and they'll be also cooperating on the project. So,
what are some of the permitting issues?
Well, at the DJ plant, it involved notification of the Wyoming DEQ, so it's the quantity that's actually being removed here is very small. So it's not a re-permitting of the plant. Now, if you were to build a commercial scale plant, then clearly that's a re-permit. We think this is a notification with DEQ and let them know. We think that's the process based on Wyoming.
And there are a number of issues that, local issues, but for the most part, EPA is very enthused about this. They are very much aware of this process. They are enthusiastically supportive of trying to demonstrate that this works. So our budgets are shown here. I don't know if you want to, so the Rocky Mountain Power portion of this, well, you can see so we have a DOE project which is funded now. It's just under $4 million project, and it goes over the time span that you see here. The Rocky Mountain Power portion of this, well, the whole project, the last 2 years that you see there aren't funded yet, but the first 3 years are. And so we spend some time in the first year making some modifications, do most of the testing in the second, and a little bit of cleanup in the third year. You can see where the budgets fall out there in terms of where they're being spent.
What does pre-run budget mean?
So before we actually do this long test run, there's a bunch of work that we're doing to things that we've learned in the Dave Johnston plant, for example, that we want to make more reliable. We want to re-engineer a couple of components of this process. And so that's the budget in doing the engineering and testing prior to the long-term
equipment mods.
Right, equipment modifications. So these are some of the questions that came. I don't know.
Yeah, so I was going to say that we're about ready to move into the DPU's questions, but in terms of the cryogenic carbon capture, is there anything else that we need to?
Have you tested this technology on a gas-fired power plant?
Yeah, well,
okay, the first set of the DPU's questions was explain in detail Rocky Mountain's participation in the study. This was on the Carbon Safe project, and how will the $150,000 be spent? I think we answered that in a fair amount of detail. There's more. If we didn't?
Yes, you're good.
DPU questions, carbon capture. Regarding the co-funding of sustainable energy solutions, cryogenic capture technology, what is the total anticipated cost of the project? And the total project cost is about $6.06 million, and our portion is the $1.17 million. And I think the next question actually gets into a little bit more detail on that particular topic. So, Larry, do you want to talk through about where your other participants are in terms of that total project cost?
so this outlines the little over $6 million total project costs. Everyone on there is committed at this point, and we are moving forward with the exception of Rocky Mountain Power pending the approval of this process. So DOE is the major contributor through the National Energy Technology Laboratory. Sustainable Energy Solutions and Tri-State and EPRI have the contributions that you can see there, and we are hoping that Rocky Mountain Power's budget would be approved and ready in time to start spending in January of next year.
So again, how much will Pacific Corp pay? That's the $1.17 million. What portion of Pacific Corp's fund commitment is allocated? So our commitment is contingent upon approval through this process. And the last question is, when was the company first approached by SCS regarding the project? Actually, the reverse in this particular case is true. We saw that this fund was available. It seemed like a natural fit to use this fit to kind of further the CCC technology. We've been following CCC's technology since early 2008, and we hosted them at the DJ plant for, I don't know, it was a 2-week test. Only took, Kyler, you were there for the duration. You enjoyed December in Glen Rock. So that's kind of our history with SCS, at least a short history. So, questions? There are 2 other clean coal technologies that we're going to bring forward, and I think it's anticipated that we would kind of piggyback on a meeting that's going to be held January 24th. That's related to looking at CO2 for getting gas, natural gas in the local area of Emery County, and the other is evaluating solar thermal at the Hunter plant for, to displace coal burning. So that's what we want to bring those up in January. Those projects are actually getting funded further along in this 5-year cycle, so we didn't think we needed to get it right in front of you today, but that's why we kind of left it off. We didn't want to give you 5 projects today. That shows no mercy.
So the question is, those topics are not referenced in the schedule for that technical conference in January 24th, I think. It was our intent that we would just kind of piggyback those, as Ian said, into that technical conference. But the question is, should we propose modification to the schedule that addresses those?
I think that would be appropriate if the parties can informally stipulate and then file one submission to the commission requesting that we amend the notice.
Okay. To address those issues, and it would be to address those issues in the January 24th.
And they should be relatively short. We should be able to take care of most of them in 45 minutes to an hour.
Among the parties, does that work? Everything's good. We'll talk, we'll have probably get on.
Well, thank you everyone
Thank
for
you.
coming. If someone from Rocky Mountain Power will please email Carol or me a copy of this presentation, we'll get it posted at the commission's website. And if there's nothing else, we'll close the conference.
Thank you.
So you're now known as the merciful